Think of a matrix as an organized machine made from rows and columns. Each entry has a precise address, just as each part in a machine has a location. A matrix can be square, like 2 rows by 2 columns, or rectangular, like 3 rows by 2 columns. We write a general matrix as A equals the array of entries A sub ij with m rows and n columns. The first subscript I tells us the row, and the second j tells us the column. So A sub 2 3 means the entry in row 2, column 3. The order m by n means m rows and n columns. Two matrices are equal only when they have the same order, and every corresponding entry agrees. Addition and subtraction require the same order, because entries must pair with entries. Scalar multiplication is simpler. Multiply every entry by the scalar. For example, multiplying a 2 by 2 matrix by lambda multiplies all 4 entries by lambda. Matrix multiplication has a different matching rule. An m by n matrix can multiply a p by q matrix only when n equals p. The inside dimensions must match, and the result has the outside dimensions, m by q. Keep that rule visible. It is the basic compatibility test for matrix machines. Matrix types are names for visible patterns. A square matrix has the same number of rows and columns. A diagonal matrix has zeros away from the main diagonal. A scalar matrix is diagonal, with the same value repeated on that diagonal. The identity matrix is the special scalar matrix whose diagonal entries are all 1. It acts like the number 1 in multiplication. A row matrix has only 1 row, while a column matrix has only 1 column. A null matrix has every entry equal to 0. Triangular matrices are also recognized by one side of the diagonal. In an upper triangular matrix, every entry below the main diagonal is 0. In a lower triangular matrix, every entry above it is 0. The notes also introduce periodic, idempotent, nilpotent, and involutory matrices. A periodic matrix satisfies a to the power k plus 1 equals a. An idempotent matrix satisfies a squared equals a. A nilpotent matrix satisfies a to some positive power p equals the 0 matrix. An involutory matrix satisfies a squared equals I, so it is its own inverse. These equations are not merely labels. They let us predict powers and eigenvalues without multiplying repeatedly. For example, the rotation matrix has 4th power I, so its 5th power is itself. The principal diagonal gives us the trace. For a square matrix A, the trace is the sum of the entries from the top left to the bottom right. Trace of A equals A11 plus A22, and so on through ANN. The trace is linear. The trace of A plus B equals the trace of A plus the trace of B, and the trace of CA equals C times the trace of A. A useful cyclic property is trace of AB equals trace of BA. For several factors, we may cycle the factors without changing the trace, although we must not arbitrarily reorder them. The transpose, written A superscript T, interchanges rows and columns. Applying transpose twice returns the original matrix, and the transpose of a product reverses the order. AB transposed equals B transposed A transposed. For complex matrices, the transpose conjugate or dagger transposes and complex conjugates every entry. It satisfies AB dagger equals B dagger A dagger. Next, distinguish singular and non-singular matrices. A singular matrix has determinant 0 and cannot have an inverse. A non-singular matrix has non-zero determinant and does have an inverse. The adjoint is the transpose of the cofactor matrix, and the inverse formula is A inverse equals adjoint A divided by determinant A. The identity relation adjoint A times A equals determinant A times I explains why this formula works. Special matrices are defined by how they respond to transpose or conjugate transpose. A symmetric matrix satisfies A transpose equals A, so entries reflected across the diagonal match. A skew-symmetric matrix satisfies A transpose equals negative A. That forces every diagonal entry to be 0, because an entry would have to equal its own negative. Every square matrix can be decomposed into a symmetric part, 1/2 of A plus A transpose, and a skew-symmetric part, 1/2 of A minus A transpose. For complex matrices, a Hermitian matrix satisfies A dagger equals A. Its diagonal entries are real because each must equal its own complex conjugate. A skew Hermitian matrix satisfies A dagger equals negative A, so diagonal entries are 0 or purely imaginary. If A is Hermitian, multiplying by a real scalar preserves Hermitian structure, while multiplying by I produces an anti-Hermitian matrix. Orthogonal matrices satisfy A transpose equals the identity, so A transpose is A inverse. Their rows and columns are mutually orthonormal, and their determinant is +1 or -1. Unitary matrices use the dagger instead. A dagger equals the identity, so A dagger is A inverse, and the determinant has unit modulus. These families matter because their structure controls eigenvalues. Symmetric and Hermitian matrices have real eigenvalues, while real skew-symmetric matrices have eigenvalues that are 0 or purely imaginary. Now we reach the central idea. A matrix usually changes both the direction and the length of a vector. But some non-zero vectors are special. After the matrix acts, they remain on the same line. The matrix may stretch them, shrink them, or reverse them, but it does not send them to a new direction. We write that relationship as AX equals lambda x. Here, x is a non-zero eigenvector, and lambda is its corresponding eigenvalue, also called a characteristic root. Moving the right side to the left gives AX minus lambda x equals 0. Because x equals IX, we factor the expression as A minus lambda I multiplied by x equals 0. A non-zero solution exists only when A minus lambda I is singular, therefore its determinant must vanish. The matrix A minus lambda I is called the characteristic matrix. Its determinant, viewed as a polynomial in lambda, is the characteristic polynomial. Setting that polynomial equal to 0 gives the characteristic equation. The important workflow is therefore, build A minus lambda I, compute its determinant, solve for lambda, and then solve a homogeneous system for each eigenvalue. We will apply every step to the same upper triangular matrix from the notes. Let us calculate the eigenvalues of our matrix A. Since A is upper triangular, subtracting lambda from the diagonal gives A minus lambda I equal to the matrix with diagonal entries. 1 minus lambda, 2 minus lambda, and 2 minus lambda, while the entries above the diagonal remain 2 and 3. The determinant of a triangular matrix is the product of its diagonal entries. Therefore, the characteristic equation becomes 1 minus lambda multiplied by 2 minus lambda multiplied by 2 minus lambda equal to 0. In expanded notation, this is 1 minus lambda times 2 minus lambda squared equals 0. A product is 0 when at least one factor is 0. The first factor gives lambda equal to 1. The repeated second factor gives lambda equal to 2, with algebraic multiplicity 2. So the eigenvalue list is 1, 2, 2. We can verify the result using the trace and determinant. The trace of A is 1 plus 2 plus 2, which is 5, and the sum of the eigenvalues is 1 plus 2 plus 2, also 5. The determinant of A is the product of its diagonal entries, 1 times 2 times 2, which is 4. The product of the eigenvalues is 1 times 2 times 2, again 4. These checks confirm the calculation. Notice how the triangular form makes the first half of example 9 especially efficient. The diagonal entries already reveal the eigenvalues. We now find the eigenvector for lambda equal to 1. Write x as the column vector with entries x1, x2, and x3. The equation ax equals x becomes 3 scalar equations. The bottom equation is 2x3 equals x3, so x3 must be 0. The middle equation is 2x2 plus 3x3 equals x2. Since x3 is 0, this reduces to x2 equals 0. The first equation then imposes no restriction on x1, so let x1 equal k. Every eigenvector for lambda 1 has the form k times the column vector 1, 0, 0. Eigenvectors can be multiplied by any non-zero scalar, so we choose a normalized representative. The normalization condition is x dagger x equals 1. For this real vector, that becomes the conjugate of k times k, which is the absolute value of k squared, equal to 1. Choose the positive real value k equal to 1. Thus, the normalized eigenvector is x1 equals the column vector 1, 0, 0. Check it directly. Multiplying a by x1 selects the first column of a, which is 1, 0, 0, exactly x1. For lambda equal to 2, the equations reduce to x1 equals 2x2, while x3 is free. To match the notes, choose x3 equal to 0 and let x equals k times the column vector 2, 1, 0. Its squared length is 4 absolute k squared plus absolute k squared, or 5 absolute k squared. Setting this equal to 1 gives k equal to 1 over square root of 5, hence x2 is 2 over square root of 5, 1 over square root of 5, 0. Direct multiplication confirms ax2 equals 2x2. The primary example also illustrates several general facts. The sum of all eigenvalues, counted with multiplicity, equals the trace. The product of all eigenvalues equals the determinant. For our matrix, the repeated eigenvalue 2 must be counted twice, so the sum is 1 plus 2 plus 2, and the product is 1 times 2 times 2. If lambda is an eigenvalue of a, then k lambda is an eigenvalue of ka. If a is invertible, 1 over lambda is an eigenvalue of a inverse. If m is a positive integer, lambda to the power m is an eigenvalue of a to the power m. A diagonal, upper triangular or lower triangular matrix has its diagonal entries as eigenvalues. Similar matrices have the same eigenvalues, which is why diagonalization is useful later. A nilpotent matrix has only 0 eigenvalues, because if a to the p equals 0 and ax equals lambda x, then a to the px equals lambda to the px, forcing lambda to be 0. For an idempotent matrix, a squared equals a, so lambda squared equals lambda, therefore every eigenvalue is 0 or 1. Real symmetric and Hermitian matrices have real eigenvalues, while real skew-symmetric and skew-Hermitian matrices have 0 or purely imaginary eigenvalues. Orthogonal and unitary matrices have eigenvalues of absolute value 1. These statements turn structural information about a matrix into quick predictions about its spectrum. For instance, the Notes' matrix with every entry equal to 1 has eigenvalues n, 0, 0, and so on. The all ones vector is stretched by n, while vectors whose entries sum to 0 are sent to 0. The eigenvalue rules let us evaluate expressions involving matrices without computing the full matrix expression. In the Notes, A is the upper triangular matrix with diagonal entries 1, 3, and -2. Therefore, its eigenvalues are 1, 3, and -2. Consider 3a cubed plus 5a squared minus 6a plus 2i. For each eigenvalue lambda, apply the scalar polynomial 3 lambda cubed plus 5 lambda squared minus 6 lambda plus 2. At lambda equal to 1, the value is 3 plus 5 minus 6 plus 2, which equals 4. At lambda equal to 3, the value is 3 times 27 plus 5 times 9 minus 6 times 3 plus 2, 81 plus 45 minus 18 plus 2, which equals 110. At lambda equal to -2, the value is 3 times -8 plus 5 times 4 minus 6 times -2 plus 2 -24 plus 20 plus 12 plus 2, which equals 10. Thus, the eigenvalues of the matrix expression are 4, 110, and 10. We can also use trace and determinant as quick checks in smaller problems. For the matrix, the trace is -7 and the determinant is 10 minus 4, or 6. The pair -1 and -6 has sum -7 and product 6, so those are its eigenvalues. In another Notes example, a matrix of order 3 has trace 13 and determinant 36. The combination 9, 2, 2 has sum 13 and product 36, so the largest eigenvalue is 9. Always check whether the matrix is triangular or whether trace and determinant give enough information before expanding a characteristic determinant. The Cayley-Hamilton theorem says that every square matrix satisfies its own characteristic equation. This means we may calculate the characteristic polynomial in lambda and then replace lambda by the matrix A, while replacing the constant 1 by the identity matrix. Use the notes matrix B equal to its characteristic determinant is the determinant of expanding gives lambda squared plus 5 lambda minus 14 equal to 0. Cayley-Hamilton therefore gives b squared plus 5b minus 14i equals the 0 matrix. This relation is useful because it reduces higher powers of b and can produce an inverse. Rearrange it as b squared plus 5b equals 14i. Multiply by b inverse, assuming b is non-singular. The left side becomes b plus 5i, while the right side becomes 14b inverse. Therefore, b inverse equals 1/14 times b plus 5i. Substituting the actual matrix gives b plus 5i equal to, so b inverse equals. Note 714. You can verify by multiplication that b times this matrix is the identity. The theorem also explains why an idempotent matrix has only 0 and 1 as eigenvalues. Its equation is lambda squared minus lambda equals 0. For the diagonalizable matrix P with p squared equal p and trace n-1, the eigenvalues are 0 or 1, and the trace forces 1, 0 and n-1 ones. Since one eigenvalue is 0, determinant p equals 0. Rank measures how much independent information a matrix contains. The rank is the order of the largest square submatrix with a non-zero determinant. Equivalently, there must be at least one non-zero minor of that order, while every minor of the next larger order must vanish. The zero matrix has rank at least 1. A non-singular n by n matrix has rank n. Also, the rank of a product cannot exceed the rank of either factor. Let us work through example 18. First, take A equal to 3, 2, 1, 3, 4, 5, 1, 2. Its determinant is 3 times 6 minus 4, minus 2 times 0 minus 20, plus negative 1 times 0 minus 15. This is 6 plus 40 plus 15 equal to 61, which is non-zero. Therefore, the entire 3 by 3 determinant survives, and rank A equals 3. Now take B equal to 2, 1, 1, 0, 3, 2, 4, 3. Its determinant is 2 times negative 9 plus 8 minus 1 times 0 plus 4 plus negative 1 times 0 minus 6. That is negative 2 minus 4 plus 6 equal to 0, so rank B is not 3. We then search for a 2 by 2 minor. The upper left block has determinant 2 times 3 minus 0 equal to 6, which is non-zero. Therefore, rank B equals 2. The method is a progression. Test the largest possible determinant first, then descend until a non-zero minor appears. Diagonalization changes the coordinates so that a matrix becomes diagonal. Suppose A has distinct eigenvalues lambda 1 through lambda n, and linearly independent eigenvectors x1 through xn. Place those eigenvectors as the columns of a matrix P. Then the diagonal matrix D is P inverse AP. In the new coordinate system, the action of A is easy. Each coordinate direction is simply multiplied by its corresponding eigenvalue. The notes illustrate this with A equal to 0, negative I, m, 0. Its characteristic equation is the determinant of negative lambda, equal to lambda squared minus 1. So the eigenvalues are 1 and negative 1. For lambda 1, solving ax equals x gives x1 equals negative ix2 and x2 equals ix1. Choose x1 equal to k and x2 equal to ik. Normalization gives the squared length 2 absolute k squared equal to 1, so k equals 1 over square root of 2. The normalized eigenvector is 1 over square root of 2, I over square root of 2. For lambda negative 1, the normalized eigenvector is 1 specific I over square root of 2. Put them into P. Its inverse is the conjugate transpose because these columns are orthonormal and P inverse AP equals the diagonal matrix 1, 0, 0, 1. Once A equals PDP inverse, powers become A to the K equals PD to the KP inverse. The same change of basis gives exponential A equals P exponential DP inverse, and logarithm A equals P logarithm DP inverse whenever the logarithm is defined. A linear transformation is a rule that maps vectors from one vector space to another while preserving addition and scalar multiplication. If T is linear, then T of alpha plus beta equals T of alpha plus T of beta, and T of C alpha equals CT of alpha. Combining these gives the defining property T of alpha plus B beta equals a T of alpha plus BT of beta. The notes write this as a mapping from a domain to a range. Each input vector is sent to an output vector by the transformation rule. A matrix is a convenient representation of a linear transformation. For example, the left sides of the three equations, 2x1 plus 3x2 minus x3, 5x1 plus 6x2 minus 3x3, and x1 plus x2 plus x3 can be collected into a matrix product. The coefficient matrix is 6, 3, 1, 1, 1, and multiplying it by the column vector gives the output vector y. Thus, Tx equals y. To verify linearity in the note's two-dimensional example, take T of xy equal to was for vectors alpha and beta and scalars a and b. Substitute the combined coordinates. The first component becomes 2ax1 plus 2bx2 plus 3ay1 plus 3by2. The second becomes 3ax1 plus 3bx2 minus 4ay1 minus 4by2. Separating the a terms and b terms gives a T of alpha plus bt of beta. Therefore, T is linear. Matrix multiplication is not just notation, it is the computational mechanism for applying a linear transformation. Rotation matrices are a concrete application of linear transformations. In the xy plane, rotating the coordinate axes about the z-axis by an angle theta changes the coordinates of the same geometric vector. The notes give x prime equals x cosine theta plus y sine theta, and y prime equals negative x sine theta plus y cosine theta. In matrix form, the coordinate change is x prime y prime equals cosine theta, sine theta, negative sine theta, cosine theta, times xy. This matrix is orthogonal, its determinant is 1, and its eigenvalues are e to the I theta and e to the negative I theta. In 3 dimensions, rotation about the z-axis keeps the z-coordinate fixed, giving the 3x3 matrix with the 2x2 rotation block and a final diagonal 1. Rotation about the x-axis keeps x fixed and uses the yz block cosine theta, sine theta, negative sine theta, cosine theta. Rotation about the y-axis keeps y fixed and uses the xz block cosine theta, negative sine theta, sine theta, cosine theta. Now apply the notes clockwise 45-degree rotation to the vector p equal to, for a clockwise coordinate change, use cosine 45, negative sine 45, 0, sine 45, cosine 45, 0, 0, 0, 1. Since both sine and cosine of 45 degrees equal 1 over square root of 2, the first coordinate is 1 over square root of 2 minus 2 over square root of 2. Or negative 1 over square root of 2. The second is 1 over square root of 2 plus 2 over square root of 2, or 3 over square root of 2. The third remains 1. Thus, the transformed coordinates are negative 1 over square root of 2, 3 over square root of 2, 1. The final section connects matrix structure to systems of simultaneous linear equations. Write a system with coefficient matrix A and right-hand side vector B. The augmented matrix C is formed by appending B as one extra column. The rank comparison gives the complete consistency test. If rank A equals rank C, the equations are consistent, meaning at least one solution exists. If this common rank also equals the number of unknown variables, the solution is unique. If the common rank is smaller than the number of unknown variables, there are infinitely many solutions because at least one variable remains free. If rank A and rank C are different, the system is inconsistent and has no solution. The simplest two-variable examples make this visible. The equations x plus 2y equals 4 and 3x plus 2y equals 2 have different slopes, so they meet once. This is a unique solution. Solve quickly. Subtracting the first equation from the second gives 2x equals -2, so x equals -1, and then y equals 5/2. The equations x plus 2y equals 4 and 3x plus 6y equals 12 represent the same line, so there are infinitely many solutions. Their augmented rows are proportional, and rank A equals rank C equals 1, which is less than 2 unknowns. Finally, x plus 2y equals 4 together with 3x plus 6y equals 5 has proportional left sides, but incompatible right sides. The coefficient rank remains 1, while the augmented rank becomes 2, so the equations are inconsistent. In larger systems, the same logic applies. Compare the rank of the coefficient matrix with the rank after appending the constants. Let us collect the toolkit. A matrix is an array whose order counts rows and columns, and whose multiplication requires matching inner dimensions. Structural names, such as diagonal, triangular, symmetric, Hermitian, orthogonal, and unitary, tell us what a matrix can do. Trace adds the principal diagonal, transpose swaps rows and columns. The dagger also conjugates, and a non-zero determinant is what allows an inverse. Rank is the largest order of a square submatrix with non-zero determinant. A linear transformation preserves vector addition and scalar multiplication, and a matrix represents that transformation. For eigenvalues, begin with ax equals lambda x, rearrange to a minus lambda I times x equals 0, set the characteristic determinant to 0, and solve for non-zero eigenvectors. In our central example, the eigenvalues were 1, 2, and 2, with normalized eigenvectors, and 0. Trace and determinant, check the result. Cayley-Hamilton lets a matrix satisfy its own characteristic equation, which can simplify powers and inverses. Diagonalization changes coordinates, so the matrix acts by simple diagonal scaling. Finally, rotations in linear systems show why these ideas matter beyond notation. When you see a new matrix, ask 3 questions. What structure does it have? What vectors does it preserve? And what rank information does it carry?